All right, welcome back to Étale cohomology on October 22nd, 2020. So last time we talked about the Étale fundamental group extremely quickly. So maybe I'll pause and ask, are there any questions about that material or anything else we've covered in the course so far? We've been speeding up because I actually do want to get to the Weil conjectures before the end of the semester. Yeah, I mean, I think it's, it's good to ask a question if you're feeling like we sped up a little too much. All right, well, so let me just remind you briefly where we were last time. So last time we finished with an equivalence of categories between LCC sheaves on X8 and the category of finite discrete pi1 Étale modules. And then we said that so under this equivalence, a module M goes to a sheaf FM, and maybe I think I kind of alluded to verbally what this functor is, but maybe let me say what it is explicitly, and then I'll restate the theorem from the end of last time. So can anyone tell me how to explicitly write down this sheaf given a pi1 module M, and how to go from a pi1 module FM to a sheaf? So if you're not sure how to do it, now would be a great time to ask a question about it. Or maybe to go the other way. And this should be, by the way, this should be sheaves of modules of abelian groups. All right, so let's say how to do it. So suppose I have an LCC sheaf on X Étale, so it's locally constant. So in particular, it's locally representable, and it's a sheaf, so it's in fact representable, right? The sheaf, the data of a sheaf gives you gluing data. So it's locally so it's representable. So let's go to F. F is represented, so it's represented by a finite Étale X scheme. And I just sketched verbally the proof of that. So it's locally constant. So locally that's true. It's locally represented by a disjoint union of copies of X. And then you use the restriction maps to create gluing data. And that gluing data, that descent data, is effective because it's, descent is effective for finite maps. And now once you have this, well, a finite Étale X scheme is a finite pi1 set by the definition of the Étale pi1. Okay, and now what does the module structure come from? The module structure comes from, or the structure of an abelian group on the set comes from comes from Uneta. So F itself has that structure, and then all the constructions here are functorial. So can anyone tell me how to go the other way? So it's sort of built into this description.
Don't we get a torsor from like our pi1 module or something like that?
Yeah, so a pi1 module is in particular a pi1 set, right? So given a pi1 module, you get a pi1 set just by forgetting the module structure, and a pi1 set is the same as a finite Étale X scheme. And now you can just take the functor represented by that. So let's call this finite Étale X scheme Y sub M. It's the Y scheme X associated to M. And you can just look into Hom dash YM. So that's a sheaf. Okay, and why is it a LCC sheaf of abelian groups? Well, it's LCC because it's represented by a finite Étale X scheme. So in particular, it's such a thing as locally trivial in the Étale topology. So for example, you can take the Galois closure of that covering and pull back to that, and that will split it. And why is it a sheaf of abelian groups? Well, it's because your pi1 module itself is an abelian group. And again, all these constructions are functorial. All right. And then given this data, we said that there was a map HI of, so continuous group cohomology, pi1 étale, M to HI of X étale, FM. And in order to describe this, I gave you a different description of this functor of this correspondence above. So the proposition was that there's a map like this, and that it induces an isomorphism for I equals 0, 1. If X is connecting. Okay, and since I went very quickly through the proof, I just want to say a little bit more. So what I remarked is that there's a map from the étale site of X to the so-called finite étale site of X. So the category, sorry about that, the category whose objects are finite étale X schemes and morphisms or morphisms over X. This map of sites just comes from given a finite étale X scheme that is an étale X scheme, right? So there's a map of, there's a functor going the other way. And what I claimed is that there's a, so this category finite étale has a growth unique topology where just covers our surjections. So more or less every map from a non-empty scheme to any other scheme is well, that's not quite true. So maps are surjections. There's covers are surjections. That's what I would say. And the claim is that there's an equivalence of categories. So finite étale X is just equivalent to the category of finite continuous pi1 étale sets. Okay, and now it's a general fact about group cohomology, which is not totally trivial. I'll say a word about it. That that sheaves on this latter site, finite continuous pi1 étale sets are just the same as continuous pi1 étale sets. So maybe let me actually just say it this way. So sheaves of finite abelian groups are the same as continuous pi1 étale, continuous discrete finite pi1 étale modules. By the way, this idea is very closely related to some kind of fancy stuff that's happening now. So thinking about instead of thinking about finite continuous pi1 sets, thinking about just continuous pi1 sets, so like pro-finite sets, for example, within action of pi1, looking at sheaves on that category is very closely related to like the category of anima that some fancy people have been thinking about recently.
Sorry, okay. What does it say next to the sheaf thing?
Sheaves of finite abelian groups, sorry.
Sorry.
Yeah, sorry about that. Let me make that a little bigger. Sheaves of finite abelian groups. Okay, so this is more or less the same proof. This claim is more or less the same proof as the claim that a sheaf on spec K étale was the same as a Galois module. It's really literally the same argument. Okay, and then now where does this map come from? So this is just the map from HI finite étale X M. So I claim that this was continuous group cohomology, which just follows if you believe in this equivalence of categories. So this is just the pullback map. Let me call this map pi. This is pi star HI finite étale. Sorry, this is HI X étale. Pi star M. Okay, and then I argued you could compute, you could show that this was an isomorphism in low degree using the Loret spectral sequence for this map. So in other words, one wants to compute Ri pi lower star, and the claim is that if you have a sheaf of this form, pi upper star m, this equals 0 for I equals 1. So that was what I quickly sketched at the end of last time. And I'm not going to do it again, but I wanted to recall this because I think I went a little too fast and open the floor for any questions about it. Okay, so the main corollary of this, which we said at the end of last time, is that we can compute a little bit about pi1 étale directly using Étale cohomology. So in particular, we can compute h1 of pi1 étale x bar with coefficients in some module m just by computing it, the Étale cohomology of x with coefficients in m. And this is something we sometimes know how to do, right? So in particular, I claimed for you earlier that the fundamental group of the affine line over a field of positive characteristic was not topologically finitely generated, and I proved it to you conditional on this corollary. So now we have an actual proof. Okay, and explicitly what this tells you is that it's not so hard to, for example, compute like maps from this into abelian groups. So if you take M to be a trivial pi1 module, this H1 is just homomorphisms from pi1 into M. So that tells us something that fairly explicit about pi1. All right. Are there any questions about that? All right. If not, I want to move on. So I want to start by briefly sketching the sort of main finiteness theorem we're going to use.
So if M isn't trivial, the action, is it normally fairly easy to see like what the sheaf like should be on X?
Oh yeah, sorry, this should be an FM. When you say fairly easy, I mean like I gave a recipe up here, I guess. But do you mean like to compute its values on an Étale?
Yeah, like computing the actual cohomology.
Yeah, I mean it kind of depends how the sheaf is given to you and how the Étale morphism is given to you. Like if you have a normal scheme, for example, it's basically just Galois theory, right? Like you're asking like you can what you can do is
I guess it's very context dependent.
I'm sorry.
Sorry, I guess it's very context dependent.
That's right. Yeah, but I mean, what you can do is just restrict everything to the in the normal setting. You can kind of just restrict everything to the Galois group of the generic point, right? And then what are you asking? Well, you're asking like you have a set with an action by that group, and you're asking what are the fixed points of the action. So okay, like in real life, it's probably pretty hard to actually get your hands on that. But I can imagine sort of situations where everything is explicit enough that you can actually do that.
Thanks.
Yeah, I mean, in ultimately, when one does computations like this, you always are doing like a billion devisages until you get into some very simple situation where you can actually compute.
Okay.
Yeah. I mean, like for example, when we computed the cohomology of curves, like we did a huge amount of work until we were able to get ourselves into a pretty simple situation. All right, so I want to spend a little bit of time on kind of the main finiteness theorem we're going to use. So ultimately, this theorem is going to be this, and the Grothendieck-Lefschetz trace formula will be the main input to proving rationality of the Bayes zeta functions. So we're finally kind of getting there. So let me state the theorem. So suppose that X is a variety over K, which is a separably closed field. And suppose that F is a constructible sheaf on X étale. Then under the following two circumstances, so one, if X is proper, or 2, if the stalks of F all have order prime to the characteristic of K, then, so if one of these two conditions are satisfied, then the Étale cohomology, HR of X Étale F is finite. All right. So first of all, can anyone give me an example showing me that these hypotheses are necessary?
A1 and just Z mod P.
Yeah, exactly. So our universal counterexample shows these hypotheses are necessary. All right. So proof. So first of all, 1 we actually already know. So can anyone tell me why 1 is true?
Just proper base change.
Yeah, exactly right. So it was one of the in fact one of the statements, one of the parts of the statement of proper base change. Thank you, Ollie. Okay, and then 2, I want to sketch the proof. So it's going to be an induction on dimension. So induction on dimension. So it's in step 0. It's true in dimensions 0 and 1. So we haven't quite proved it in dimension 1. We've more or less proved it in dimension 1. I mean, in fact, yeah. So strictly speaking, we will actually prove it in dimension 1 via this argument. I just want to point out, like, so in fact, for the induction step, all we're going to need, sorry, for the base case of the induction, all we're going to need is dimension 0. But we've more or less proved it in dimension 1 in the sense that we've proved it for smooth curves. And then you need a little bit more argument to get it for singular curves, but it's not so bad given what we know, for example, about, for example, you can reduce to the normalization. All right, and now I'm going to sketch the proof under the assumption that X is smooth. And I think at the time when this was proven, that assumption was not a reasonable one in the sense that we didn't know, well, we still don't know how to do resolution of singularities in positive characteristic. Now we know it in, but now we have the alterations theorem, which I think should make the reduction to the smooth case much easier. But I'm not going to say anything about the reduction, and I'll just prove it in the case X is smooth. So this is not part of the proof. This is just a simplifying assumption to make the proof more accessible. All right. So now 2, I'm going to assume X fits into an elementary fibration. So maybe I'll just write X equals U, fits into an elementary fibration. So I have, so what does that mean? I have U living inside of Y. Its complement is Z. So this is open. This is closed. This is Y minus U. This maps to some S. This is smooth and proper of relative dimension 1. This is finite étale. And this open map is fiber-wise dense. Can anyone explain to me why it's okay to assume this?
Are we going to use purity of some kind, or?
We're going to eventually, but I mean that'll be in this setting. So I want to know, how do I reduce the general case of smooth X to the case of something fitting into U fitting into an elementary fibration? So I'm trying to show the cohomology of X is finite. Is it enough to show that why is it enough to show that is that for things coming from an elementary fibration? Any thoughts? So it's not so obvious. So you need a little bit more than we have, unfortunately, and I didn't want to spend a huge amount of time on this, but the idea is so you can cover X by things fitting into an elementary fibration, right? Do you guys agree with that? So that was part of Arden's, that was part of the theorem about the existence of elementary fibrations. And then the idea is you want to use check cohomology, or the check to derived spectral sequence to compute the cohomology of X using the cohomology of U. Okay, and the obstruction is that the intersections might not fit into an elementary fibration. So we need to think a little bit, right? So it's we suppose we know finiteness for these U's, we still don't know the finiteness for UI cross UJ over X, but okay, you can still cover those by things that fit into elementary fibrations, and then you would have to use something called you'd have to use a hypercover. So this is one approach, but let me not say more than that. I claim that there's a pure homological algebra way to reduce to this case. All right. Are there questions about that? I'm happy to say more if there are questions, but it's my claim is that this is pure homological algebra. All right, so let's now prove this case. So we're in this setting. So now one has to do some dévissage to reduce to the case where F is LCC. Okay, and then maybe you would replace U by another elementary fibration. So this is a Geisen argument. So this is you stratify, you look at like an LCC sheaf by its very definition is locally constant on a big open, and you take that big open and use these Geisen sequences to relate to the complement. So we're going to assume F is LCC. Okay, and now finally, so we now have an LCC sheaf on one of these U's, and we'd like to understand it. So what we're going to do is we're going to look at the Loret spectral sequence. So let me call this, I think I called this F before. So we're going to look at HI S with coefficients in RJ, F lowered star of our locally constant sheaf F. All right, so what's next? Any thoughts? So this is going to converge to HI plus J of U with coefficients in F, which is what we're trying to show is finite.
Can we look at the stalks of RJ, like try to compute it using it?
Yeah, so maybe your idea is to say, well, okay, let's actually try to compute. So it's enough to show by induction on dimension that RJ F lowered star F is constructible. For all J. Do you agree? Or does anyone have any thoughts on that? All right, cool. All right, so let's think about it. So how are we going to compute RJ F lowered star? Any thoughts? So let me give this map from Y to S a name H. So this F is H composed with I. So we're going to compute it that way. So we're going to use the composition of functors spectral sequence. So we get a functor, we get a spectral sequence RS of H lower star of RT I lower star F, which converges to RS plus T of F lower star of capital F. So this just comes from factoring the map F as the composition of I and H. So we can study these functors separately. So first of all, so the main observation, so observation 1 is that H is a proper morphism. Right, so that was part of the definition of an elementary fibration. So in order to show that these objects are constructible, it's enough to show that Ri lower star F is constructible. So that this is just by proper base change implies that it's enough to show that that Rj of I lower star of F, so the derived push forwards from U to Y, are constructible. Okay, so now our goal is finally, it's reduced to the following claim. So we have U embedded in Y, and here we have, let me redraw the whole picture. So this Z is Y minus U. So this is a smooth proper curve. And this is finite étale. And I think that implies the rest of this is open and this is closed. I think this implies all the properties we need. So it's enough to show that in this situation, taking the derived push forward of a locally constant sheaf is constructible. Does everyone agree with this, or does anyone have any questions about why that's the goal, or why that's enough? So at the risk of sounding like Jeb Bush, somebody please say something just so that I know I haven't completely lost everyone. Okay, I'm getting at least one thumbs up.
It was fine.
Okay, cool. Okay, so now what happens? So now let me just briefly explain what happens in the case where F is constant. So F is actually constant. And one can reduce to this case if one wants. So first of all, what is I lower star of F? So here, let's say F equals lambda underline. So what is I lower star of F? So it's I lower star of lambda. So what is the push forward of a constant sheaf from an open to the thing it's dense in?
Just constant sheaf on the whole thing.
Yeah, so this is lambda on Y. Great. So that's certainly constructible. Then what about R1 I lower star of lambda? Any thoughts? Does anyone have any guesses, actually? Let me give this a name. So this is a non-trivial exercise. So I claim this is more or less purity, as Ollie mentioned earlier. So this is the push forward along this morphism J of some constant sheaf. So it's, in fact, it's some twist of lambda. of lambda twisted by a question mark. Okay, that's certainly constructible. So this is a restatement of purity from before. So this is why we had to get ourselves into a situation where we had a kind of a smooth pair. Okay, so this is certainly constructible. Can anyone at least argue for me that this is yeah. So can anyone explain why this is, maybe just to test your understanding, why this is supported on Z?
It's an isomorphism on U, and therefore
Yeah.
it's exact.
Great. Okay, perfect. Okay, so we know it's supported on J, and then you're going to use purity to try to understand what's happening along Z. Okay, and then finally, I claim that R iota lower star lambda equals 0 for I bigger than 1, and that this is again a restatement of purity in this situation. And they could mention one case. Okay, and now we're done. All right, so here's a question for you to test your understanding. Where did we use the hypothesis that the order was prime to the characteristic? Anyone? So I claim it was precisely in this step. Okay. So this uses order prime to characteristic. And maybe one nice thing for someone enrolled in this class to do would be to volunteer to present this exercise. So if you've been following the course, hopefully this is something you can do in office hours next week, say. So I encourage people to prepare for that. All right. So this is the sketch proof of fineness. Are there any questions about that before we move on to other things? Okay, so strictly speaking, let me kind of tell you what's missing. So here I sketched this in the case where X is smooth. So what's missing are the devisage steps to the case where F is LCC, and then also the reduction to the smooth case, which you can try to do using alterations, for example. The proof in SGA4 is quite different from this. So this is a sort of serious modification of what's done there. Great. Okay, so now I want to talk about sheaves of ZL modules. So ultimately, let me just remind you of sort of what the goal of this course is. So the goal is to count some points on curves, or not just curves, sorry, varieties over finite fields, right? And what we're going to be, the way we're going to do that is we're going to understand some Frobenius actions on cohomology and take their traces. And if we want those traces of having a chance of counting something rather than counting, let's say, mod a billion or mod L to the billion, we have to be able to have those traces live in a ring in which no non-zero integer equals 0, right? So far we've only discussed sheaves with finite stalks, and that's not going to be enough. Like if your cohomology groups are finite, then you've no chance of actually counting anything except modulo a large integer. So now I want to describe sheaves of ZL modules, which will be the formalism we use to compute in excuse me, to compute in kind of characteristic 0. All right, so a sheaf of ZL modules is not a sheaf. So what is it? So let me give you the definition. So what it is it's going to be a sequence of sheaves Mn along with maps Fn plus 1 from Mn plus 1 to Mn. So this is a sheaf of ZL modules in an abusive notation. if the following is true. So first of all, each Mn is a constructible sheaf of Z mod L to the n Z modules. Okay, and B, so each Fn plus 1 induces an isomorphism Mn plus 1 modulo L to the n times Mn plus 1 to Mn. So in particular, this says that, well, L to the n times n plus 1 is necessarily in the kernel of Fn plus 1 because Mn was a map of Z mod L to the n, was a sheaf of Z mod L to the n modules. So L to the n here goes to 0 here. So Fn automatically induces a map like this, and the requirement that this is that this is an isomorphism. All right, are there any questions about the definition? So what's the motivation for this? So the motivation for this is that if you have a complete sheaf of ZL modules, then you can figure out what it is just by reducing mod L to the n for all n. Sorry, let me back up again. If you have a complete ZL module, then you can figure out what it is just by reducing mod L to the n for all n. And completeness tells you, maybe let me actually write this down. So the motivation is that given a complete, an L complete ZL module, n, we get that n is the inverse limit of n mod L to the n, capital N. So this is just what it means to be complete. Okay, and what that tells us is that we can determine n. So it means the data of n is kind of the same as the data of n mod L to the nn with the transition maps. All right, and so here what we've done is we've just imitated this data. So this is like saying we have a complete sheaf of a complete kind of sheaf of ZL modules. And at least part of the goal here is like ZL has a topology, which would somehow intervene in the picture if we tried to work directly with sheaves of ZL modules in a way that we wouldn't really know how to understand. I mean, people now know how to understand it, but this was not the original formalism. And so this is a way of sort of forgetting about the topology and only remembering kind of discrete data, namely these quotients and the transition maps between them. All right, are there any questions about the definition? Maybe let me give you an example. So the sort of obvious example is you could take Mn equal to the constant sheaf Z mod L to the nz for all n, and then Fn plus 1, which would be a map from Z mod L to the n plus 1 Z to Z mod L to the nz is the obvious map, quotient map. All right, so this sheaf here has a really nice property, which is that well, if you look at the stalks, they're all Z mod L to the n, and if you take the inverse limit of those, you get a torsion-free, or in fact a free ZL module, namely ZL, right? So that's the next definition. So a flat or lease sheaf of ZL modules or sorry, if this is just a flat sheaf of ZL modules, so I'll say lease in a little bit. A flat sheaf of ZL modules is one such that the following holds. Excuse me. So in addition to the above, the above, so there's a sequence, ms, then multiplication by L to the n gives you a map to m n plus s. I'll say where this comes from in a second. And this maps to mn just by taking the composition of the transition maps. And we want this to be exact. Okay, so where does this come from? So mn plus s maps to ms. So it's a quotient, but if you think about what happens when you multiply by L to the n, so that's in the kernel of this map, and if you think about it for a minute, you'll see that induces a map back. Yeah, in other words, there's a sort of natural splitting here. Okay, so the condition is that this is exact, and this is again motivated. So the sort of motivation for this definition is that this exactness characterizes flat L complete ZL modules. All right, so this is what a sheaf of ZL modules is. So let me tell you now the main definition. So the reason we care about these things. So what's the cohomology of such a thing? So suppose that MFN is a sheaf of ZL modules. So the main definition is, well, we want to take the cohomology of such things. And what is it? Well, it's just the inverse limit of the cohomologies. Where the transition maps are induced by the maps Fn plus 1. And then we can also take compactly supported cohomology. It's the same thing. We take the inverse limit of the compactly supported cohomologies. All right, let me give you an example. So suppose X is a smooth proper curve of genus G over field, so over K, which is separably closed. And has characteristic not equal to L. So then we can take the cohomology of X Étale with coefficients in just the ZL sheaf ZL. So this is the one where you take Z mod. This is the example from before where you take Z mod L to the n to be Mn. So this is the inverse, by definition, this is in the inverse limit of HI, HI X Étale Z mod L to the n. And so can anyone tell me what this is? So we know these groups are, let's see what happens in I equals 0, I equals 1, and I equals 2. And we know that for I bigger than 2, the groups we're taking the inverse limit of are 0. So we got 0. So what happens in I equals 0?
It's going to be ZL.
Yeah, we just get ZL. So each term is just Z mod L to the n Z. So we're getting the inverse limit of Z mod L to the n Z. What about I equals 1?
You get the limit of L torsion and pick.
Yeah, so if I did mu n, if I did mu L to the n instead of ZL, I would get the limit of L torsion and pick. So if you'd like,
It's like twisted by -1.
Yeah, that's right. So what you get is the Tate module, the L-adic Tate module of the Jacobian of X twisted by -1. Great. And what about I is 2?
ZL again?
So it's again, there's a twist. So
Oh.
so it would be
-2.
nope.
Oh,
So if it was -2, that would have weight 4, right?
that's right. Yeah,
So what is it?
should be -1.
Yeah, it's the same. It's the same twist as before. So if you'd like, I mean, what happened is we computed with mu L to the n before, so that would give us a ZL of 1 here. So we're just twisting everything by -1.
Yeah, that's right.
Cool. Glad you guys agree. All right. Are there any questions about that example?
What weights? What is that?
We'll get to it later. Sorry. Yeah. It's
Okay. Yes.
yeah.
Sorry.
That's something from the. It's saying that we want this. We want the zeta function of this curve to satisfy the Riemann hypothesis. So weights are a fancy way of talking about that, but it's a good way to remember what things have to be. Sorry, I said weights to Sasha because we've chatted about it before, so I know he knows about it. Yeah, if you haven't heard of weights, don't worry, you'll hear about them in a couple weeks, hopefully. All right. So okay, so here's let's discuss the properties of these cohomology groups. So these look pretty nice. I mean, let's say just like abstractly what these are. So this is as an abstract group, and forgetting about the Gell action coming from functoriality, this is just ZL to the 2G, right? So here we get a one-dimensional thing, we get a 2G dimensional thing, and a one-dimensional thing, and that's good. Like that's what the cohomology of a smooth proper curve of genus G is supposed to look like, right? All right. So right. So let me state the main theorem. So the main theorem is that if M is a flat sheaf of ZL modules, on a variety X over K, which is separably closed, then if X is proper, or L is not equal to the characteristic of K, then two things hold. So one, there's the Étale cohomology of M, or the L-adic cohomology, is finitely generated in ZL module. And B, there's a Long-Zat sequence, which goes as follows. So there's a Long-Zat sequence HR minus 1 X Étale MN, which goes to HR of X Étale M. And this goes via multiplication by L to the N to HR X Étale M. And finally, this goes to HR X Étale MN. All right, so this is the statement of the theorem. So this is a finiteness theorem. And then it says, moreover, that one can directly relate these inverse limit cohomology groups to the cohomology groups of the finite pieces. So you're supposed to think, so the thought bubble here is that this Long-Zat sequence associated to the shorter Zat sequence 0 to M, sorry. Did I screw up these orders? Oh, no, I didn't, okay. 0 to M to multiplication by M, multiplication by L to the N to M to Mn. So this is what you're supposed to think about this Long-Zat sequence. There's not really a sense in which this Long-Zat sequence literally exists, right? What really one does is one builds it out of these short exact sequences in the definition of flatness. Okay, so the proof I'm not going to give. It's a good exercise, but what I'll just say is, so one, you reduce to the finite quotients, so reduce to the previous finiteness theorem. This is a very doable exercise. And then two, you build the long Z sequence above out of the long Z sequences in cohomology, arising from the earlier long Z sequence in the definition of flatness. So ms to m n plus s. So this was multiplication by L to the n, and then mn to 0 by taking the inverse limit, by taking the limit as s goes to infinity. Okay, and there's actual content here. I mean, this inverse limits are not exact, so there's a little bit of content one has to think about. All right, are there any questions about this? So this is an exercise you should try. This is much easier than the previous exercise, and again, this is maybe something, if you feel like coming to office hours and presenting it this coming Monday, I think that would be great, especially if you're enrolled in the course. All right, are there any questions about this? Okay, so then finally, let me make a definition. So a ZL sheaf M Fn plus 1 is locally constant. This is, again, a locally constant ZL sheaf is neither locally constant nor a sheaf, but I'll say a word about that in a second. So it's defined to be locally constant if each Mn is locally constant, constructible. Well, it's a ZL sheaf already has constructible built in, so locally constant means just LCC in this case. And then we say it's least if it's flat and locally constant. So least is a French word that means smooth, but you should really just think of it as saying it's a local system. All right, are there any questions about this? Okay, so here's the warning. So suppose M Fn plus 1 is locally constant. So this does not imply that there exists a cover of X such that it's constant. So okay, so if we had an actual an actual LCC sheaf, the definition is that there's a cover where you pull it back and then it's constant and it's constructible. Right. So can anyone tell me why this is not true for ZL sheaves?
Like down the line, you could just need more and more fine covers.
Yeah, exactly right. So you can find some cover trivializing Mn, but you might need to refine it more to have a cover trivializing Mn plus 1, and then so on and so forth. And that genuinely happens. So let me explain a little bit about what's going on. Let me briefly discuss pi1 representations associated to, I guess, excuse me, to locally constant ZL sheaves. So suppose you're given a locally constant ZL sheaf. So suppose M M equals Mn Fn plus 1 is locally constant ZL sheaf. ZL sheaf. Then for each n, we get a representation. We get a representation rho n from the Étale fundamental group of x with your favorite geometric base point x bar into aught of the fiber of Mn at x bar. Can anyone tell me why this is? So Mn is a LCC sheaf, right? And we said at the very beginning of today and at the end of last time that such things are the same as finite discrete pi1 modules, right? And this is what it means to be a finite discrete pi1 module. You have a continuous map into the automorphism group of a fiber, right?
Mhm.
Great. All right. And moreover, these things live in a tower. So given an automorphism of Mn plus 1, well, if you reduce it mod L to the n, that's a characteristic quotient. So you get an automorphism of Mn. All right. So what this means is that that locally constant ZL sheaves are the same as continuous representations. So what this says is that locally constant ZL sheaves are the same as continuous representations of pi1 étale on finitely generated ZL modules. And then least ZL sheaves are the same as continuous representations of pi1 étale on finitely generated flat, also known as free ZL modules. Okay, so what we're saying is that least ZL sheaves are the same as representations of Étale pi1. Right, but okay. So what is the condition that a locally constant ZL sheaf is actually locally constant in the sense that there exists a cover trivializing it? It's more or less the same as the condition that this representation has finite image. Okay, at least in the normal setting, that's the case. So that's a very rare situation. Like in real life, you don't a real representation that shows up will very rarely have finite image. Maybe I will try to give you examples of those soon. I think we don't have quite enough to compute.
When we say flat here, do we just mean like a regular algebraic flat, or like
flat
tensor product?
Flat we defined it was this sort of exact sequence being, it was this exact sequence here being exact.
But for the pi1 modules.
Yeah, sorry. I mean, it's a condition of on the module underlying module, so it's flat as a ZL module. But a finitely generated flat ZL module is just the same as a free ZL module.
You know, because like, so like flat, like being like tensor product being exact. I was wondering whether I because I'm doing continuous things, I would need to like sort of be thinking about.
No,
completing my tensor product somewhere.
You don't need to worry about that for the finitely generated things.
Okay. Yeah,
that's a good question. I mean, yeah, you should check that. So exercises. Convince yourself that a finitely generated flat ZL module is in fact just as an abstract module no topology is in fact free. And my hint is that all you have to use is that ZL is Noetherian and local. Okay, cool. So that tells you, so being flat as a discrete module is much easier to check than being flat as a topological module. All right. So finally, let me briefly discuss the notion of QL sheaves. So I'm not going to define the category because it's a little complicated. So what it is it's the category of QL sheaves is the localization of the category of ZL sheaves at L. But what I'm going to do is I'll define the cohomology of a QL sheaf of a ZL sheaf. Sorry, of a a QL sheaf for us, just the underlying object will be it'll just be a ZL sheaf plus the word QL. So what I mean by this is that a ZL sheaf, an underlying objects, it's just the same on underlying objects, a QL sheaf is just the same as a ZL sheaf. I guess I can tell you what a morphism is. Why not? So a QL sheaf is just a ZL sheaf. Sorry, I changed my mind. So a morphism of QL sheaves is a morphism as follows. So it's let's say we have M and N. So it's a morphism from M prime to M, where this has finite kernel and co-kernel, and a morphism like this of ZL sheaves. So that just means a morphism level wise. So in other words, what you do is, if you've seen, I don't want to spend a lot of time on the categorical formalities, but if you've seen Serre subcategories, you localize at the category of the Serre subcategory consisting of ZL sheaves, all of whose elements Mn have bounded order is a Serre subcategory, and that's it's a subcategory you can formally set equal to 0, and that's what you do. Okay, so given but I think we're going to be able to get away with only thinking about the objects. So you can just think of the objects of the categories being the same as a ZL sheaf. So given a ZL sheaf, a QL sheaf M, which we're going to just think of as the same as a ZL sheaf, we define HI x Étale M to be the same thing as before. So the inverse limit from before. And then we just tensor with QL. And then again, HI compactly supported Étale M will be the same inverse limit from before. And then again, tensor with QL. All right. Great. So the point is that if you have a morphism like this, it's going to induce an isomorphism on these groups. So you can think of it as being what we're doing is we're formally adding in inverses to morphisms like this.
Is this in any way related to sort of like looking at abelian varieties, like up to isogeny and stuff?
Yeah, so the isogenate category is exactly a version of this. So what you do there is you take the category of abelian varieties, and then you formally invert all morphisms which have finite kernel.
Mm-hmm.
Yeah, so it's exactly the same story. So if you've seen that, then then this should be familiar. Yeah. So I mean, I can tell you, maybe let me, because I feel like I always feel guilty when I give a non-definition like this. Let me just verbally tell you what the definition is. So there's a little bit of work involved in making sense of this, which is that the localization of a category at a Serre subcategory. So here, the localization of the category of ZL sheaves at the category of finite ZL sheaves is the universal category through which any functor of abelian categories, which kills your subcategory of finite things factors. Okay, and there's a little subtlety there because it's a two categorical thing, but that doesn't really sound fun to spend the next 8 minutes talking about. All right, are there any questions about that? Great. Okay, and then finally, let me remark. So before we said there was an equivalence of categories between between locally constant ZL sheaves and locally constant QL sheaves. So I claim that given a a QL sheaf whose underlying ZL sheaf is locally constant. We get a continuous representation, pi1 étale, bar into GLN QL. And in fact, there's an equivalence of categories. So in fact, this is an equivalence of categories. So can anyone tell me how to go the other way? So I've been vague about what this category is, which is why I'm not going to prove this. But let's just see if we can make a map going the other way. So how would you go from a QL representation of pi1 to a QL sheaf? So there's actual content here, although it's not, you know, it's not. I just want to make sure. Oh, go on.
Can we like look at like maps going into GLN of like ZL to the N, and then like sort of.
Yeah. So the issue is that this is a representation into GLN QL. There's no reason it should factor in through GL and ZL. Right.
But like, so isn't our thing like totally disconnected? And
our thing.
Meaning, it's no, but it's GLN QL. So okay, no.
Yeah. So given row is above the claim, and it is more or less a purely topological claim, but I just want to make it explicit because it is content. So the claim is that row is conjugate to a representation into GLN ZL. And this is a good exercise. So it's an exercise using the fact that pi1 étale is a profinite group. But let me just say, I'll verbally give two proofs. So proof one is that pi1 étale is compact. So the image in GLN QL is compact. And one can classify the maximal compacts of GLN QL, and they're all conjugate to GLN ZL. Okay, so that just begs the question: how do you classify the maximal compacts? So let me say a word about that. So what you do is you pick any lattice in QL to the N. So pick ZL to the N. So proof sketch here. So take ZL to the N inside of QL to the N. So it's a topological claim. Is that the stabilizer of ZL to the N in pi1 étale, and by the way, this is true for any profinite group, is open, hence finite index. All right, so why is that? We'll just pick a generator of ZL to the N, look at the stuff that sends it into ZL to the N. That's an open condition. There are finitely many generators, and so you've taken a finite intersection of open subgroups, and so you win. And they're not empty because the identity, it's not empty because the identity's in it. Okay, so we have this finite index subgroup stabilizing ZL to the N. So now we take the sum over G in the cosets of the over the cosets of the stabilizer. So G in pi1 modulo the stabilizer of G times ZL to the N. So this is now obviously stable under pi1 étale. And it's finitely generated because this was a finite sum. So which implies it's isomorphic to ZL to the N. So that's a little commutative algebra argument. So the commutative algebra fact you need is that any finitely generated torsion-free ZL module is free. All right, and now we're done. So we've now pick a basis of this lattice. So that gives us a conjugation into GLN ZL. And now, well, we said earlier that least ZL sheaf was the same as a representation into GLN ZL. And that was the argument Ollie was saying, where you reduce mod L to the n and to get the finite pieces. All right. Are there any questions about that? All right. Well, if not, we have 2 minutes left, and I don't want to start a new topic with so little time. So maybe I'll stop recording. And thank you all for coming.